Okay, here they served up a lovely question about a circle that we're given in this form to begin with, and we've got to, they tell us the method, we've got to complete the square to get it into this form. The x squared isn't doing us any harm, we can leave that alone, but the y squared minus 10y, I would take that on one side and deal with it separately. Y squared minus 10y get us expressed as a squared bracket with something off the end, standard method for completing the square from chapter 1, and then apply that and substitute it in, get the constants onto the other side of the equal sign, and you should end up with this. Once you've got this in this standard form, then this becomes chapter 4 theory. You've got to remember how the coordinates of the centre of the circle, C, are shown in this equation, and how to read off the radius of the circle. So you need to look probably on the front of your chapter 4 booklet for the standard equation of the circle to remind yourself how these pieces of information appear there. They're only 1 mark each because they come straight off the standard knowledge of the standard equation. Okay, then in part C, more interesting things happen. We've got a line with equation y equals 2x, okay, and we've got to look at, point of intersection. That means we're looking for simultaneous equations. And it's for the line and the circle, so we need an equation for the line and an equation for the circle. You've got a choice of 2 equations for the circle. This one might be slightly simpler, but this one you know is absolutely correct. But either of these will work. What you've got to do is substitute one equation into the other, and look, we're given an endpoint. This is a show that question, so we're going to end up with that quadratic equation. Don't get mesmerised by that to begin with. You'll only see that appear when you've done the point of intersection method using the 2 equations. Alright, but because it's show that and we've got an endpoint, it means that this is a re-entry point here. We don't need to have been able to set that up in order to show that the line is a tangent to the circle. What we do need to know is how to find the coordinates of the point of contact P and show that it's a tangent once we've got this equation. If you're in doubt about how to show it's a tangent, then leave that till after you've got the coordinates of the point of contact. We know that this equation applies to any points of intersection, so you solve it to find x values. Now, a quadratic equation will normally have 2 x values, and with each of those you can go back to one of the original equations, preferably that one I think, and find the corresponding y values. But for a tangent, you're not actually expecting 2 separate points. So when you solve your quadratic equation, you comment on the number of solutions you get. And the direct way to show that it was a tangent was actually to consider the discriminant and use the value of that to say it's going to be a tangent. Doesn't really profit you in this case, because you've got to go on and solve it anyway. So the number of x solutions is your way into showing that it's a tangent. Make sure you comment on that. And your x value together with the corresponding y value are the coordinates they want. On to part D. If we were trying to prove that the point Q was on the circle, we'd verify that the coordinates worked in the equation. But because we want it to be inside the circle, that's not the way to go. Don't try and do this by substituting values into the equation. Work with distances. We know the centre of the circle in terms of coordinates, and we know the coordinates of Q. So we need to work out the distance from C to Q. So use your 2-point method from chapter 3, first method in chapter 3, to work out a distance, and then compare that with the radius, and that will convincingly show you whether the point's inside or outside the circle.